routine of 30 days of machine learning. We have covered a lot of exciting problem statements in the last 14 days. I think we started from the very baseline, which was logistic regression, and then we moved on till autoencoders. And very exciting to discuss everything related to the problems, all of the maths, the code, and the intuition to get an absolutely good idea. And we should keep continuing with it. So that brings us to day 15, which is today. And let's see the problem that we have on our hands. Adult income classifications. So this is a very exciting problem because there is actually no new model that we are implementing today. It is just another method in ensemble learning. So for those who haven't watched it, we discussed ensemble learning in quite a lot of detail in one of the earlier videos, and I will make sure to attach the link of that video in the description today, so you can go and check it out. So whenever we talk about ensemble learning, two of the most famous types that come to mind are bagging and boosting respectively. They are basically the ones which are the most known. So that is fine. And the thing is that bagging and boosting are very widely discussed. Random forest is a type of a bagging model. Then for boosting, we discussed XGBoost, we discussed gradient boosting, then light gradient boosting machine in a lot of detail. So those two are the most famous ones, most popular ones, because they are, technologically, they're very sound models to use. Stacking is sort of like the black sheep. It is like the hidden horse in ensemble learning, but it is still used a lot, and which is why I decided to include it in today's problem statement. And we'll approach it from the basic intuition and then go on to the problem and basically discussing the math used in stacking. Eventually, then we'll discuss the code, our usual pipeline of going through things. So let's go through the problem without wasting any time. What do we have? So we have a Kaggle adult income dataset. It is a massive, massive dataset. I think there were about 40-50,000 samples in the dataset. So they are basically asking us a very simple problem. This is a type of problem statement which has been repeated in this series a lot of times, and it is again a binary classification problem. Basically, they want us to classify between two things. So we have an adult income data set. You can check it out from Kaggle, and they want us to classify whether the individuals, the adults in the data set, earn more or less than $50,000. Okay, so there are some features given, some independent features, and based on them, we have to predict or classify a dependent feature, which is the income. So sounds like a pretty typical problem statement. I think we started with logistic regression for the binary classification problem, and then we tried out multiple ones. So we'll go through this slowly. Okay. So this is some information about the data set. You can go through the data set as well. We will be doing the EDA shortly, but I decided to list some of the important stuff here. So after data cleaning, there were about 48,000 entries. So this is like I said, a massive data set compared to what we usually do. 14 raw features, and there are some missing values which we had to encode, of course. This is class 0 and 1. Basically, there is a slight class imbalance. So we basically had to classify the income into two parts: less than equal to $50,000 and greater than $50,000. So these are the number of people having their income as less than equal to $50,000. This number right here, 37,000. Okay, and 11,500, those are the number of people who earn more than $50,000. Okay, this is what's given to us. So now, without wasting any time, first we'll discuss a short part of the code so that you understand what data set we are dealing with today, and then we'll go on to solving the main problem. Okay, basic stuff. Come on now, I'm not even going through this. Pandas and NumPy, these are our standard imports. We import time because we measure the inference latency and the training time of every model. Okay. Again, till now we haven't really gone through deep learning, any deep learning. So all of the machine learning stuff is available in sklearn. That is our bread and butter library. So train, test, split, standard scaler for the scaling. We'll discuss it again, but standard scaler I've discussed multiple times. K-fold, I'll be discussing it. These are some of the models that we have tried to implement. Okay. Grid search CV for the hyperparameter tuning, so that we can have a exhaustive hyperparameter tuning. that we can do in the model. And these are some of the metrics that we try out. This is all pretty typical. So this is how we move on with the pipeline. This is basically the path of the CSV file that we have, the adult income CSV. So what you can do is you can download the CSV and you can save it here. Then you can copy the path and enter it between these quotes right here, and your model will run. PD.read CSV, typical. Now we get on to the EDA. So as usual, I have commented out the EDA because it doesn't really contribute in building the model. It is basically for us to see how the data looks like. Okay. So we look at the shape, it will give us all the typical values that we got. Okay, 48,842 and 14, because shape is basically the number of rows and columns in the data. Okay. And when we move forward, df.describe, it gives us the statistical values. You can run all of these and check them out. This is, we have done this multiple times, so I'm not wasting any more time on this. This df.isNull.sum basically gives us a sum of all the missing values in the data set. So there were no missing values in the data set. There are nan columns, which means columns which are having nan values, NA, not applicable values, or question marks, but not really any missing values. This is a hist plot, which means a histogram for the income, and we plotted this because we wanted to know how the income distribution is. So you can look at this. This is the same thing that we were discussing here, that there is a slight imbalance in here. So 37 with less than 50,000 and 11,000 something with greater than 50,000. The same is displayed here. Okay, so this is a cool thing to do. You can do this because see this table won't be available when you are building a model on your own. So these things, that whether a class imbalance is present or not, these are important into eventually selecting what model we are going to use. So you need to find these things out on yourself before going on jumping to the model. The EDA, this is why I stress upon it every time, because it is super important to even decide how the data is behaving, what the data looks like, because that leads to us deciding the model for the problem. So this is the income class distribution using the hist plot. Okay. Then very importantly, these were our numerical columns, age and all these columns. So you can look at them as well. Let me skim through the EDA quickly. So, this is our feature correlation heat map. We have been doing this for a long time. So these are the features having numerical values, and this is a correlation heat map, which is why which basically means it is going to give us the values between correlations of these features. So age is going to be 100% correlated with itself, which is why this value right here is 1. Then the correlation of age and this FNL WGT feature is something in negative, so they are not highly correlated. Basically, the darker this color is of the boxes, it basically points to a higher correlation between the two features. Okay, so this heat map is also very good, and to get the numbers inside the heat map, there is a keyword called anot. See, anot is equal to true. This basically leads to number inside the heat map, and this is basically CMap coolworm. Okay, this is the dot as type keyword in Python. It basically applies this thing on the entire column. So this num calls contains all of the numerical columns, okay, in our data set, and we want to make a heat plot out of it. So we won't be taking each and every feature individually, which is why we apply this dot as type on this entire column, and this is the size of the figure that we are using in this case. Now moving forward, what else do we have? This is the heading, basic. Now moving on to the data pre-processing. Like I said, in the data there are not really any missing values, but there are some question marks. And come on now, no model understands question marks. It will be confused. It will be like, what does this question mark mean? So we need to deal with them. And there was one other problem. This data set is consisting of some empty spaces, some white spaces, some blanks in the headings, in the values as well. So we need to deal with them, because see, whenever these white spaces are present in the text, it leads to mismatches, because the machine doesn't know that it needs to ignore the white space. It will take the white space as a string, it will take the white space as a part of the data, and that will lead to mismatches that we don't want. Okay, so you can keep reading it alongside. This is basic stuff. So we strip the white spaces using the dot strip function. Again, we apply dot as type because we want to strip the white spaces from all the columns. So this as type basically allows us to apply this dot strip function to the entire column at once. Okay. Wherever there is a question mark, we replace it with a np.nan, basically giving it an empty value so that the model now understands that specific cell, that specific row and column has an empty value. And then we drop the empty values. Okay, this is how we have handled the pre-processing part. Now the encoding comes in. So we had to classify in two ways. So our income could be less than equal to $50,000 or greater than equal or greater than $50,000. So we have encoded it as 0 1, basically like a binary encoding. And in some of the columns, the 50K had a dot after it. See this. Now this less than equal to 50K dot and less than equal to 50K is the same thing. But this was a slight bug in the data set, so we had to deal with it. And basically what we did was we assumed them to be the same thing. So less than equal to 50K and less than equal to 50K dot both have been assigned to 0, which means that this is the 0 class and this is the 1 class. So this is basically, we are trying to make binary classes for our data set. Now these are our numerical columns. So this is simple as well. Now very importantly, there was one small thing. Some of these numerical columns were having string values. So again, numerical, age cannot be a string, right? Age is a number. But the thing is, this data set is a bit flawed in that way. It consisted of some of the string values. So we really had to convert those string values back to the numerical columns. So we again described these numbers, okay, these columns as the numerical columns, and we iterated through them to convert them to numeric values. So pd.toNumeric is the keyword to do so. Move forward. Now, very simple categorical feature encoding. Again, something we have been doing for so long. So basically the features which have got some categories in them. So we don't really want to, keep all the categories. So we encode them using one hot encoding. So this is basically applying the one hot encoding. pd.getDummies does that. And we drop the first is equals to true because we want to avoid the multi-collinearity trap. So the multi-collinearity trap is very simple. Let's say you have got black, white and gray, three colors. Okay, now I tell you that the color that I have is not black and it's not gray. So what will it be? It will be white automatically. See, there is no need to have the white column. My point is that if you want to encode three features, it can be done using two, because if it's A and if it's B, then it cannot be C. Simple as that. So if I'm saying that my color is not white, my color is not gray, then automatically it will be the third color, the leftover color. Which is why we try to avoid this trap of using three variables. Okay, this is why this drop first is equals to true is used. Okay, this is basically the x and y that we make the independent and dependent data. So income is the dependent data that we are predicting, and except that all of the features will be the independent features. See, x and y. So this is it. Now from the scaling, again you can see the scaling as well. It's common for all the models. The train test split is so that brings us to the intuition of stacking. So we have discussed how we implement the usual pipeline very quickly because there is nothing new to discuss till now. Now, I'll be starting from scratch and then trying to, make sense as to what stacking is and why we have chosen it as our model today. So, we can say it very simply that our problem today is a binary classification problem, like the ones that we have discussed it till now. Let me mention it quickly here. Binary classification. Simple. Okay, so for binary classification we know multiple models that we can use. We have so much stuff that we can use for binary classification. Now let's just assume that we are using multiple models to solve this problem. Let's assume, because we have multiple choices. Let's say that we have four models that we can use to solve this problem. Okay, let's assume. I will show you the training and how it is done, but first of all, we need to get an idea deeply about the intuition. So let's say we have got four models, okay? So they are like four experts. So for model one, I have got logistic regression, okay? Typical for binary problems. For model two or expert two, I have got a KNN model based on distances. Now for model 3, let's say I've got an XGBoost model because the data set is big, so XGBoost is also pretty suitable. And for my expert 4, I have got a random forest model. Okay, typical, right? This is like nothing new. We do use these models all the time. Now, let's assume that when we trained these models, they gave us some confidence score. Now, what is a confidence score? It is basically a value telling us how confident these individual models are in predicting the output. So let's say that the logistic regression gives us a confidence score of I don't know, let's say zero point 0.4. Okay, and the KNN gives us some confidence score, whatever, it can be anything, let's say maybe zero point 0.7. XGBoost gives us a confidence score of 0.88. Okay, and random forest gives us a confidence score of 0.6. Okay, these are confidence scores, which means that, let's say if I want to say it as an example, for random forest, a score of zero point 0.6 will mean that it is 60% confident in predicting the correct output, whatever that output may be. Okay. So now my question to you is, you have these four experts, these four models, and you have their confidence values. Now, which of these values, which of these models will you select as your final answer? Now, straight away, typically anyone would say that we should go for XGBoost, and it is sort of the correct answer because we have a tabular column, because we have a tabular data set, and our entries, our samples in the data set are less than 10 million. So XGBoost is tailor made for this problem statement. But the thing is that we are not exactly trying to go for an XGBoost problem, and there is a reason for that. The thing is that these values that we have right here, these ones, they are confidence values. They are not correctness scores. They are confidence scores. Let me write it down here. They are confidence values. Basically, they are trying to signify the confidence that we have in the models. Okay. Confidence scores or values. Okay. Now, tell me something. Will you trust the confident model straight away? Will you trust any model which is confident straight away? Now you might say yes, but the answer to that is no, and there is a reason for that. You see, these confidence scores are basically like probability values, and they don't always resemble the correctness values. Basically, if the XGBoost model is 88% confident to map out the correct output, it is saying that I am 88% confidence I will give the correct classification, but that confidence score does not equal the correctness score. So in actuality, when I check whether it is correct or not, it might not be correct. Okay, so that is the first problem that we have. Basically we are trying to choose a single model out of these four. So and we are doing that based on the confidence scores, but like we said that confidence scores are not really a good metric, because 0.88 is like a very high score, so we can say that XGBoost here is like very confident. Okay, random forest is okay, it is above zero point 0.5, so we can say yeah, this is maybe okay. Zero point 0.7 for KNN, this is also good, and zero point 0.4 for logistic regression, we consider it as a low value. But we don't always know whether these confidence scores mean that the model is correct or not. So how do we decide that? How do we move forward? So for this, I have a very good analogy that will make us understand something, and let me quickly explain that. Now, take the example of maybe a stock analyst. Let's say that you are some person who has a massive stock portfolio, and you have a stock and you want to decide whether you want to buy the stock, any new stock, or you want to sell your old stock, and you eventually want profit. Everyone wants profit, and you're trying to decide that. Now let's say that you are the businessman or the person in question, and you go to four stock analysts. Okay, four people who are considered as experts in dealing with personal portfolios. So you go to four stock analysts. Okay. So analyst 1, okay, analyst 2, analyst 3, and analyst 4. Now, analyst 1 says buy the stock. Analyst 2 says buy the stock. Okay. Analyst 3 also says to buy the stock. But analyst 4 is saying that no, buying is going to cause you a loss. I want you to sell the stock. My experience tells me that selling is the best option in this case. Now the thing is that three out of these four analysts are telling you to sell, are telling you to buy. Okay, correction. Three out of these four are telling you to buy, but one of them is saying to sell. Now, the thing is, will you automatically trust the majority? The answer is no. Why would you not trust the majority? The thing is that whenever real world data is involved, whenever money is involved, people tend to be super careful. So the thing is that you won't go straight away by the word of the analysts, okay? Because you need some data to look at. Now you need to confirm whether these analysts are saying the truth or not. They might be experts, but I don't know that. I don't trust them basically. They're new people for me. So how do I trust them? How do I know which analyst do I have confidence in and which analyst do I know is not the correct guy for me? So how do I do that? So the thing is, let's say that this analyst one is the most confident. Okay, this analyst is, let's say, the loudest. You are in a meeting and the analyst is the loudest in saying no, 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 I want you to buy the stock, buy the stock. He's very persuasive, very loud. Now will you automatically trust the loudest analyst? The simple answer is no. The simple answer is no. What will you do? What will you do? You will go on to patterns. Okay, you will go on and you will try to find patterns in the work of these analysts. You will go on and see what mistakes have these analysts made in the past. What is their history? Have they actually made someone a profit? Which firm do they work with? You will try and find all of these intricate details about these analysts based on historical data. You will find some you know agreement patterns, where the analysts agree with you, maybe some disagreement patterns. So you will try and find these things, okay, for the analysts themselves. And the reason why you are doing this is that so that you can establish that which analyst do you trust the most. Okay, and why are you doing this? See, I'll tell you why are we doing this. There are two reasons. First of all, the reason is because of profit and loss. You cannot really trust an analyst blindly, especially one that you have not known. Okay, even if they are supremely confident, even if three of them are saying that go and buy the stock, buy the stock, buy the stock, people don't usually trust them this way because they are new people and they need to establish some sort of trust on them. So they will try and analyze these things to get to a conclusion. Okay, so this basically brings me to my point, the analogy. So the point here is that the question that we are asking should not be that who is the most confident. The question that we were asking before is that who is the most confident. This is actually not the correct question to ask. The question that we should be asking is that who has earned the most trust under circumstances. This is the question that we should be trying to ask. And the reason is very simple, because whatever decision you are going to be taking is going to be on the trust that you have on these individual stock analysts. You're not going to take them on their word and basically take a impulsive decision. Okay. And coming back to the argument about voting. So people will ask that, three people were voting in one way and one was going the other way. So why did we not go with the majority vote? And there is a reason for that. The reason is because not all of these experts are going to be equally smart. Analyst 1, 2 and 3, they might be junior analysts who are working for, let's say, 5, 10 years for a financial firm. Analyst 4 might be a veteran in his own field. So you cannot really take them on their word by voting, because basically they are not equally smart, and since they are not equally smart, they do not have equal voting power. It is just like before, in the 16th century, 17th century, only the people in the clergy and the royalty, basically, the royal family, the church, only the people in those families had the right to vote. Okay, and the other people didn't. Now we don't live in those times. We have universal adult franchise, so everyone can vote. So everyone's vote currently in the human world count as equal, right? But the thing is, for the stock analysts, someone might be more experienced, someone might be smarter, someone might be better at one thing. So we cannot take their vote as one. Okay, which is why their votes are not the same, which is why voting here is not the correct approach to go forward. Okay, so till now, did you get the point? Did you try and get the analogy that I'm getting to? Okay, this is the same analogy. Like, we had four stock analysts right here, we have got four models right here for our problem of binary classification. Question that we were asking before first is that who is the most confident, so that we can take the most confident model and move forward. But that is not the correct way, because confidence is not going to equal correctness. We need to have some historical idea. We need to actually ask this question, that who or which model has earned the most trust under the circumstances. What circumstances are those? Adult income classification, the problem that we are solving. Okay, so this basically brings me to the problem that we are solving today, the model that we are using today to solve our problem, which is nothing but stacking. Okay, so stacking is nothing but it is a method in ensemble learning. And what we are going to do in a gist, if I tell it to you quickly, what we are going to do, we have these four models, right? We are not going to use a single one of them, we are going to use all four of them. How are we going to do that? So the gist is that we are going to take like a meta learner or a head model. Okay, so we can call these models as base models. We are going to take a meta learner or a model which sits on top of these four models. Okay, and based on their confidence scores, the meta learner assigns them some value. Okay, if the confidence score of the individual base models is less, then the meta learner will penalize them, it will put a penalty on them by giving them a smaller value. And if the confidence score is high, then the meta learner will assign them a higher value, and based on that we will move forward. Okay, don't worry, this was just the gist. I will show it to you in a diagrammatical sense, in a diagram, so that everything becomes mapped out very clearly. Because stacking is not a separate model, it is just like a after we are done with the training, stacking is usually used to extract the final 2-3% of the performance metrics. Let's say you got a precision score of 80, and you are sure that applying stacking will give you a better value. Then stacking will improve the precision to maybe 82 or 83. So stacking is not really like a model you train from scratch in the beginning, it is just like a modification applied on the base models that you have trained already. Okay, so now, if you can read the formal definition in the repo as well, but I will write it. So what happens is that, if I mention it quickly, instead of manually choosing which opinion, okay, or more correctly, which model matters, we train another model whose job is to learn which expert to trust. Okay, so we train another model which is called as a meta learner in the formal language, in the machine learning terminology. And the job of that meta learner is to basically learn which model it should trust. So we have got four base models here, okay? And the meta learner will sort of sit on top of them and decide which one should I trust in which situation. So how does that look like? So let's say I've got my meta learner right here. The meta learner can be any model, but it is usually chosen as a simple model because, like I said, stacking is not complicated to a very high level. Because we are already using four base models, so the computational power required is already going to be very high. So don't choose a super complicated meta learner. It is usually like a very simple thing which is chosen. So in this case, in today's problem, we have chosen a logistic regression model as our meta learner. Okay, so this is our meta learner. Let me box it. This is my meta learner. Okay, and what it will do is it will sit on top of the four. So it will sit on top of these models, which were our base models. Okay, simple as that. And these are my individual base models or experts which we got before. Okay, and based on this we will basically be getting a final answer. So you can write like this for final prediction. Okay. So the meta learner, it's good to talk about it. So we'll discuss it a bit before moving forward first. So the meta learner acts like the CEO of a company. Okay. Let's say that this random forest is my CTO, my chief technical officer. This is my CFO, chief financial officer. This is my COO, chief operations officer. This is my CMO, chief management officer, or some sales officer, whatever. And these four are experts which are going to make certain decisions for the company. But me, I am the meta learner. And as the CEO, the final decision of majority of things still rests in my hand. So this is how the meta learner acts like. It is going to basically combine all of the predictions and produce a final output that we are going to use. Now, how does that happen? It is a simple mathematical process. So we had some confidence scores for the base models. So those confidence scores are fed to the meta learner. So these are the confidence scores. Let me just write them as P1, P2, P3 and P4 for the four base models. Okay, what were they? You can take anything because I'm just trying to prove an example. I'll take random numbers between 0 and 1 to prove what I'm trying to say. So zero point 0.8, okay, 0.85. These are confidence values for the base models. Okay, remember that. Then zero point 0.3 and then maybe a zero point 0.6. Okay, so this is a high enough confidence score. This is high, this is very low, and this is sort of in the middle around 0.5. So now what the meta learner will do is that it will identify that these values are very high, so it will try and reward them in some way. So these values are basically multiplied with weights, okay, in order to give them some value. These weights are generated at the time of training, but again for solving purposes I'm trying to take random values for weights. So let's say for this one we get a W1 weight and the value is 1.5. For this one we get another weight W2 which is 2.0. For this one we get a W3 value which is, let's say, minus zero point 0.1. Why minus? Because it is trying to penalize the lower values. This is a very low confidence score. So the weight that must be assigned to it should also be low so that it gets a penalty. This value right here, maybe you can take anything you want, maybe take a zero point 0.2. Okay. Now, or maybe just for calculation, maybe let me take this as minus zero point 0.5. Really try to put some penalty on the values. Now, moving forward, what happens now? The thing is, now we calculate the weighted sum. So basically what we do is we multiply these weights with their confidence scores and we add them up. So this is written like this if you want to write it in the mathematical terms. Wi multiplied by Pi, and then some bias term is added so that nothing becomes zero. Bias again is assigned during the training, but let's take it as -1 just for solving sake. So you multiply this, you get 1.5 multiplied by 0.8, okay, added to 2 multiplied by 0.85, okay, and so on. I'm not doing the calculation, you can try it yourself. I'll just write the final result, okay. And so the final result of this total score that we are trying to calculate comes out to be 1.87. So this is the final produced value that will go inside the meta learner. Now what was our meta learner? Our meta learner was a logistic regression model. And as we know, logistic regression uses a sigmoid function in order to get the final answer. So what does a sigmoid function looks like? It is basically something like this. Okay. This basically what it does is it pushes the value of z between 0 and 1. So that is what we are trying to achieve, because that will be like a probability value that we can interpret. So after this step, we basically input the 1.87 into this equation, and we get 0.866. Okay, if you write that in percentages, it will be 86.6%. Okay, now we will discuss what this result means, but let me just give you a quick recap as to what we have done. So this is how the stacking algorithm works. Like, you have a meta learner. The meta learner gets the confidence scores. Okay, these are the confidence scores, and they are assigned by training the model. They are not assigned manually. I have put them here manually to show you the calculation, but during the training they are not assigned manually. They are trained values. These weights are also trained values. Okay, this is called as the weighted sum. It is something we'll be discussing in deep learning a lot as well. So you multiply them and add a bias term to get this final value, which is eventually converted to a probability score using the sigmoid function. Why the sigmoid function? Because our meta learner is logistic regression, which works on the sigmoid function principle. If it was some other meta learner, we'll be using something else entirely. Okay, this gives us a confidence score or a confidence value of 86.6%. Now this basically means that the final model that we are getting has a 86.6% chance of predicting the correct class. These are not confidence scores. These are basically probability values, the final probability that we get. Okay. So what happened in the background? How did we get this value? So what happened is that our meta learner, logistic regression, took the base learner's confidence. Okay. This was the base learner's confidence right here, this P1, P2, P3 and P4, and it penalized the low confidence scores. These two are the low confidence scores. It put a penalty on them. Okay, and it rewarded the strong models so that we get a final probability value. Okay, now this basically stacking right here, this is stacking algorithm. What it does is it reduces the variance in the model and it extracts the final 1, 2 or maybe 3% of the performance that we can get. This is not going to cause a drastic change in our accuracy or precision, recall or ROC-AUC metrics. It is going to cause only slight changes, which is why I said that this is only applied after we are done training our major models. Okay, so very important statement. Let me quickly write it down. Stacking exploits variance in learning biases as base learners are mathematically correlated. Okay, so this is very important to understand. This single one liner right here, this can give you all the intuition that you need for stacking. So the thing is that we took 4 base models in this case. Like you saw, we took logistic regression, random forest, KNN and XGBoost. So now one might ask a very intuitive question, like a very simple question. Why not some other base learner? Or why not take super strong base learners? Like XGBoost is already pretty strong, but why not take other learners as well, which are, let's say, light gradient boosting machine or gradient boosting, only the strong ones. So the thing is, it does not work like that. We cannot choose similar base learners. We need to have diversity in the base learners. And the reason for that is because that diversity is exactly what stacking is trying to exploit. See, these confidence scores that we were getting, these different values that we achieve, these are based on how all of these four base learners are performing in the current situation. If except if in the place of KNN I had a LGBM model or maybe a gradient boosting model, its confidence score would have been similar to XGBoost. That way my stacking model would be able to learn absolutely nothing. See, the thing is, the one thing which is very important to understand, what happens in a typical problem statement. The thing is that this is my model, right? And the model is trained on some training data, right? Some training data. And this training data I get out of my data set, right? My data set is massive, whatever data set it may be. And I get the training data and I have got the testing data here, which I use to test it later. Now the model is trained on the training data to produce an output. Okay, and then the output is produced using the test data and both of them are compared. This is what happens, right? But the thing is that in stacking none of this is happening. In stacking, the thing is that the model never actually meets the data set. Okay, like I showed to you in the diagram, see, this is what is happening in stacking. In stacking, it is not really touching the data set at all. In stacking, it is touching this and this. So the features for the stacking model are these base models. They are not the data set that we are dealing with. So when I write stacking, what happens is that the meta learner that we are using, logistic regression, it won't go through the data set. It would be going through the confidence scores of the base models that we are using. These base models, it will be looking at them. It cannot look at the data set. It does not work like that. It looks at the values, the prediction values, the uh, you know confidence scores that we have for these models itself. So if I take these as similar, if I take these base learners as similar, my stacking model would not be able to learn anything, because all of the predictions, all of the confidence scores would look similar to each other, and the final output would mean absolutely nothing. Okay, so this is a very important reason why we need to have diversity in our base models in order to have a strong stacking output. Okay, so this is the reason why we cannot use this, and this statement now it will make a lot of sense for you. So stacking exploits the variance in learning biases. So variance in learning biases means that different models go for different learning mechanisms. KNN goes for distance based learning. Basically it will try and find the nearest neighbors, and based on that it will form its algorithm. Logistic regression finds linear patterns in the data. XGBoost is a boosting type of an algorithm, so it works by sequentially correcting the mistakes of the past model. Random forest, it is a tree based model, a bagging based model. It works with parallel trees. So all four of them, they are having different learning mechanisms, which is why they are not going to make the same mistakes. They are going to make different mistakes. Those mistakes can be learned by our stacking model, and that is what it's trying to do. This is why our model currently works and gives us a pretty high accuracy score, or a pretty high final score, this 86.6%. Okay, another analogy I can give you before moving on forward so that you can understand it. Let's say that a new cricket player, because this will be like a more understandable example. A new cricket player joins the squad or the team. The cricket player can be set as X. Okay, now I have a coach. My coach wants to know how good that cricket player is. So this is my coach right here. Coach wants to know how good the player is. Now how can I judge a cricket player? How can I judge a cricket player? I can maybe judge the cricket player by batting. I can judge the cricket player by bowling. by wicket keeping, and by fielding. These are the four typical areas. So maybe I can write it. I can write maybe by batting skill, by bowling skill, okay, fielding skill, and wicket keeping skill. Correct? Okay. This is how the coach wants, because let's say that the coach is asking that how good is this player. So I'll be asking that what do you mean? In which terms is this player good? So the coach will ask the best batter in the team. Let's say the coach asks Virat Kohli, for example, that how good is the new player. For bowling, he asks something like a Jasprit Bumrah, because he's one of the best bowlers in the world. Okay. For fielding, let's say he asks Ravindra Jadeja, and for wicket keeping, let's say he goes for Rishabh Pant. Okay. So the coach is standing there, and he's asking that I want to judge this player X. Now the thing is, the batter Virat Kohli, the batting expert, will only be able to appropriately judge this player based on their batting skill. So he'll say, okay, coach, he's maybe an okay batter. He's like not a contemporary batter, not a classical batter, but he will suffice in IPL and T20s. Let's say the bowler Jasprit Bumrah gives some input on bowling. Okay. Then Ravindra Jadeja gives some input on fielding. Rishabh Pant gives input on wicket keeping. Now, will the coach listen to only the bowler? Okay. Will the coach only go to Jasprit Bumrah and ask him, okay, tell me how the player is? No. The coach will be using the values for all four of these experts. Why? Because that is going to give the coach a broader idea as to how the player is. Because the player is supposed to have many qualities: batting, bowling, fielding, wicket keeping, and the coach really wants to get an idea. Now the batting expert can give a very good idea about the batting skill, but not about the bowling, not about the wicket keeping, not about the fielding. For them, for bowling, fielding, and wicket keeping, we need their respective experts to come forward and basically do their thing. So that is the same intuition in stacking. You cannot use a single strong model, because the other models are still contributing. They might be contributing less, but they're still contributing. So you cannot ignore their contributions. You need to give them some weight, which we try and give in our stacking model. Okay. So based on, let's say the new player is some player X, so batting skill, let's say Virat Kohli gives him zero point 0.8, which means out of 1. Jasprit Bumrah says he's an okay bowler, so he gives him a 0.3. Ravindra Jadeja said that the player is good in catching but not really ground fielding or something, so a 0.6. Rishabh Pant says the guy cannot do any wicket keeping, so he gives him a like a 0.2. Okay. So this is how we move forward. Now the coach will take the predictions, the coach will take the confidence from all four of these players, and he will form a final opinion. The coach in this case can be thought of as the meta learner that we are using, which means the logistic regression that we are using. And these four, the batter, the bowler, the fielder, and the wicket keeper, can be thought of as our base learners. So all four of them are important. Now let me quickly go on to the report to see what else do we have. Okay, so that was the intuition for stacking. Very easy to understand really. You can form your own analogies as well to understand it in a more deeper manner. So the data set, this was the pipeline that we implemented. I'll talk about it in a second. So this is the principle. You can read it. The no free lunch theorem also tells us the same thing, that no single model is universally best. So we try and take the good from each model and penalize the bad. Okay. Let's go forward. These are the four base learners. So you can see this. I'll quickly get on to this. This is the same calculation that we did. Values might be a bit different. You can try it out again yourself. See, this is a probability or like a confidence score. Then we multiply them with their respective weights, which are produced during training itself. Sigmoid squashes them to a final probability right here. Okay. What else? What else? So yeah, I'll come on to this out of fold prediction. It's an important concept. Let's see what do we have in the code. So in the code, if we move forward, we did the scaling, of course, because we are dealing with logistic regression and KNN both. So in both of them, distance is going to be calculated in the KNN, and logistic regression would basically be dominated by the larger features if we don't scale. So standard scaling is a must here. We make the train test split, and we basically move forward. So this is a helper function. Since we are implementing four base learners, there is no point in writing code for all four of them separately. So this is an efficient way to do it. So this is the start, basically used to measure the time taken to train by each base learner. This is how you model.fit to train the model. Okay, latency, prediction, the probability scores, and the metrics, and you can return this. This is how separately we have trained them. Max iterations is 1000, neighbors 15, typical. Okay, and then you can add the separate results to this result array and then return them. Okay. Now for our XGBoost model, we also went for tuning of the XGBoost model because the XGBoost has a lot of hyperparameters. So we went on to train it using grid search CV. Okay, so you use grid search CV to find the best combination of hyperparameters and then basically tried it out again. This is how we do it. See, tuned the baseline model for XGBoost. No need for that, but it's just that it's a strong model, so we use it at its maximum capability. Okay, and this is the OOS. Now, coming to the OOF predictions, the thing is OOF stands for out of fold. You can read it alongside as well, but I will be explaining it. See, the thing is that what happens is that we are training four base models. Correct. We are training XGBoost, we are training KNN, we are training random forest, and along with it, we are training a logistic regression. So the thing is that let's say that I train XGBoost on all of the data. Let's say on 100% of the data, which means the entire data, and then I try to test it. What's going to happen is that XGBoost is going to give unrealistic results. It will be like it will make me suspicious because I will be like, yes, XGBoost is strong, but how is it getting such extremely high, unrealistically good values? So that becomes a problem. To fix that problem, we have this out of fold prediction trick. So what we do is that we divide the data into k parts or k folds. Okay, we have taken it as 5 where it is sort of a universal number to divide the data. Now what we do is we train the data on four folds and we keep one fold as the holdout set. Okay, like the test set. So I train my model on the four folds, which means 80% of the data, and I keep the 20% to test, called as the holdout set or the holdout fold. Okay, and the point of that the point of this is that it prevents the model from having unrealistically good results and keeps the model honest during training. Okay, and we repeat this process k times and then take the average of whatever our final value is, and this is repeated for all four base learners separately. Basically we do this for XGBoost, KNN, logistic regression, and for the random forest. Okay, so this is a good practice to do always. It is usually a part of our stacking model. So if you want to look at it mathematically, you can read the repo. So no need to look at these mathematical symbols and feel overwhelmed. So fm of minus k basically means that the model is being trained on all the folds except k. So like we said that out of k, we have to keep one as separate and then use the k minus 1 folds to train. Okay, and then that process is repeating k times and then the average is taken. So if you look at this formula, this 1 upon k is taken to average it out, and this minus k means that one of them has been excluded. Okay. The meta learner, see, you can read about it here as well. The meta learner here is logistic regression. Never take a too complicated meta learner as it leads to absolutely nothing. Uh, Very important, very good thing to discuss about the time, space, and inference complexity. So, as I mentioned before, stacking is super computationally expensive. One of the most expensive models to ever deal with, and there is a reason because let me quickly go through it. Okay, so there's a reason for it. Let me tell you why. The reason for very very high complexity is that, if we try and see what's happening, so we are training our model for k folds, correct? K here is 5. We'll add the values later, but let's just take it as k. We have got m base models. Okay, what is m? M is basically, we have got 4 base models. Okay, k, how many folds? We have got 5 folds. Okay, and then we have got the individual complexity of all the base models. Basically, KNN is going to have some time complexity, XGBoost is going to have some time complexity, random forest and logistic regression, all 4 of them have different time complexities, and they are going to have it here. So there is going to be time complexity of the base model, correct? Now after this, we are also having n samples in the entire data set, which was I think 48,000 something that we discussed before. And and we are also training our meta learner, correct? So this is for the base model. The base model is being trained 5 into 4 20 times. We also have our meta learner, which is learning from the base models itself, correct? So it is also being trained, let's say, m times, because there are m base models. So this is what the final time complexity comes out to be. Okay. So if you write the values, this TC base is going to be different for all four models. N is 48,800 something. M is again 4. So all of the base models are being trained 20 times, and then the meta learner is being trained based on the predictions on all 4 of them. So overall, it becomes a very very computationally expensive process, which is why stacking a lot of times is not considered as a good trade-off. It is considered that it should be avoided. Okay. You can read this as well. It is the same thing. This is the space complexity. So space complexity, basically we need to analyze what the stacking model is storing. So it is storing n into m, which means all of the values of the base models. Okay. And it is still a pretty high value, but it is manageable because our base learners has random forest and XGBoost, which are both tree based models. So it is going to be storing all of the nodes. For KNN, it is going to be storing the nearest neighbors. That is how it is happening. Okay. Now the inference complexity, it's simple. Basically, we have calculated the inference time, inference latency later, which we'll discuss. But the inference complexity per sample, you can go through it. So we calculated it later, but this is not going to be a very high value. The KNN might take a lot of time. We discussed this in day 6, I guess, where we were discussing the failure cases about KNN. It does take a lot of time per query, so that is a negative point. Okay. These are the metrics we calculated, and this was the comparison table. So looking at it, if you look at the XGBoost and the tuned XGBoost, and then the result of the stacking. So the stacking is not really, beating the XGBoost. You see, look at the XGBoost right here, and then look at the stacking. The stacking is not really beating them. See, the values are near about. There is not much improvement. Okay. It's hardly there. So this is why I said before that stacking does not dramatically increase some value. It is not like a very very high level of optimization. It is just going to try and extract the last few percentages of model metrics that we can try and get, which it has tried here, but not much success in this case. Okay, only this recall value is high, 0.64, and it too gets beat by the tuned XGBoost model. Okay. This is the ROC curve. ROC curve, like I said before, the more it is towards this left corner, it means it is going to be stronger. So you can see stacking and tuned XGBoost are almost overlapping on top of each other. This purple line right here. So it means they're near about the same. Okay. This is the precision recall curve. Again, you can see the tuned XGBoost and stacking are near about the same. The KNN is definitely going to be the worst because it is the slowest. Okay. Now, a very important thing, the failure cases. So, like I mentioned that we need to be very careful, first of all, in selecting the base learners that we are using. So if our base models are too correlated, which means let's say they are all boosting models, then the stacking model is not going to be learning anything because the errors are going to be correlated. Okay. So model diversity is vital in this case. Okay. Overfitting risk is always going to be there. You can read it in the first point as well. And the primary reason is that the base models are being trained on the full training set, and we need to definitely avoid that, which we did by using the out of fold predictions. So if that is not being done, then there is no point of training the model because it is not going to generalize well. It is going to give us fake results. It's like cheating or bias in a model. Okay. Meta learner complexity is another important point. Like I said, you cannot choose a super complicated meta learner because the meta learner needs to be low capacity because stacking is already computationally very demanding. Okay. Then marginal gains, we saw this that there is hardly much improvement that we are seeing because our data set is pretty clean. So we also need to be careful with the data set by applying stacking, because the more you apply stacking, you are wasting computational power. So at one point you really need to decide the trade-off, whether wasting that computational power is worth getting the benefit that stacking is bringing. Okay. The KNN latency, you can read it. It is basically mentioning that KNN model, it requires a large amount of complexity per query, and that causes an issue to us. Okay. Now, very important, let me quickly go through the code. The code in some parts was new and it was interesting to look at. Let me scroll through it quickly. Okay. Just a second. Okay. So, what did we do? This is all typical. We did this before. This is nothing new. Let me see something which is, new. Return, logistic regression. Mm-hmm. So if you go and look at line number 143, there is a small thing to look at here if you want to interpret this line. So the thing is that, whenever we write this thing, best XGB dot predict, or basically model dot predict, it gives us the output of the final classes. See, there are two classes in this case. There is class 0 and class 1, which was less than equal to $50,000 and greater than $50,000. So the best XGB dot predict will give us the class values, but it will not give us the probability values. If we want that, we use this dot predict proba keyword. Okay. And this colon comma 1 is basically numpy slicing in order to get the correct values. Okay. This is the thing. So this basically means that give us all of the probability values belonging to class 1. Now, this is how we get it. And if you go forward, this was the latency calculation. So latency, basically the total time divided by the shape of the data. So x test dot shape, this is going to give you the number of rows or number of samples in the data, which was 48,000 something. See, again we have done this here in order to uh, get the probability values of class 1. Okay. And we wrote it here again because we had to tune XGBoost in order to get the values. This result is going to basically consist of all of our metric values. So moving forward, let me see what else is remaining. Yeah. Out of fold stacking, the code might seem a bit new. So, we take n splits is equal to 5, basically k that we took, the number of folds. So this is the training data for the meta learner. Now, like I said, that our meta learner, logistic regression in this case, is not going to see the data set. What it is actually going to see is its features, and its features are nothing but the base models that we are dealing with, which means logistic regression, KNN, then XGBoost and random forest. So to initialize the meta learner, we make an array or like a matrix having all zeros, and inside that we have these samples, whatever our sample size is, and 4 is the number of columns that we have. So wait, if I write it down, basically, we get something like n comma 4 kind of a shape. And it is all why do we write this? Okay. So what is happening in this case is that I'm trying to make the data for my meta learner, and initially that data is going to be 0. It needs to be initialized with 0 because initially we do not have a value that we can get, and we need to have zeros because numpy needs to be initialized with some sort of a value. It cannot be initialized with empty values. Okay, so this rows comma 4. So what were the rows in our data? It was something like 48,800 something. So this np dot zeros, it is going to create a row having 4 columns. Why 4 columns? Because we have got 4 base models, and it is going to make 48,830 such rows. Okay, like this. It is going to be repeated for whatever the rows are in the data set. This is what this np dot zeros does for us. Okay, this is important to initialize. Then the meta test does the same thing. Okay, very important question, why are we creating this? Because this is going to form the data, basically the features on which the meta learner is trained. To do that, we need to put the values that we train inside this. So we initialize it with zeros. These were our models. We iterate through the models one by one, and we add the prediction values of these models inside the meta learner in order to train them. Okay. So after the np dot zeros, you can come to this line. This is a very important line. This is what we are going to be doing. So when I add this, basically what will happen is that the predicted probability value that I got for the first class is going to be input inside this matrix. So if I write it down, you know let's say that the predicted class had some value of 0.83. So it is going to be input for logistic regression. Let's say logistic regression was the third one. So for the third one, we can input 0.83 in this case. Okay. This is going to happen for the logistic regression. Next iteration, it is going to happen for the KNN. Next iteration, it is going to happen for the random forest. This way it is going to continue until the training for all 4 models has been completed. Okay, this is very important to understand. I don't spend this much time on code usually, but this is completely new, how we train the meta learner. So it is initialized with zeros. Just revise it very quickly. Okay, 4 columns. Why? Because we have got 4 base learners. Okay, so 4 base learners having zeros, all 4 are going to be 0, and they are going to be appended later, like we have done right now. See, in this is what we have done. Okay, and then after we have basically input all the values of the base models inside it, we can basically take the mean and take out the final prediction, because that is what happens in the k-fold out of fold prediction. We basically take the average in the end. So this is what is happening there. Okay, then the meta learner, we need to define what it is. So the meta learner is logistic regression, and then we calculate everything back for the logistic regression again, and we add it to the model results. This is the code for comparison, easy peasy. We compare the visualizations that we made in the end. This is the code for that, basically for these visualizations, ROC curve and other stuff. So if I go back to it, these ones. Okay, uh, this is all of the predicted values. These are the same ones that I printed in the code. ROC curve. The main thing to understand, except the intuition of stacking, the thing which is worth practicing in this is this OOS stacking snippet of code. It is very important that you get hands-on with this, because this gets a little bit confusing because there are so many things happening in here. The first thing is to understand, I'm repeating it again because it is important, as to why it is initialized with zeros. See, when we have not begun the training, we need to still give it some value. Otherwise, we won't be able to initialize it. You cannot initialize an empty thing. We need to initialize it with some value. So we initialize with zeros. How many zeros? 4 zeros in one row. Why 4 zeros? Because there are 4 base models. How many rows? The same rows that are present in the data set. How many are those rows? How many rows are present in the data set? Nothing but 48,842, which in the code, if you want to write it, it is written as X shape and then bracket 0. But everything you want to know, and if you have any confusion, you can definitely read the repo. I say it all the time. The repos, they took a lot of effort to make. There is tons of information you can read inside it, and as usual I will be dropping two or at least maybe even three article links in the description itself so that everything becomes crystal clear. Okay. This is the code, and I will be linking the code in the description itself. You are welcome to check it out. And I think that will lead us to concluding today's video. Thank you so much.